Hello, this is Ms. Moore, and today during chemistry we're going to discuss bond energy. Today's essential question: what are bond energies and how are they calculated? Let's start by discussing what is bond energy. So atoms are attracted to one another when the outer electrons of one atom are electrostatically attracted to the nuclei of another atom. Remember, nucleus is positive, electrons are negative. The attraction between two atoms makes them increasingly more stable, giving lower and lower potential energies. What we're talking about here is atomic bonding. And remember, the point of bonding is to try to get to the atoms to have that stable octet, the full s&p orbitals. Okay, so that is why this attraction, while the atoms start to bond, the potential energy is lower, because that stable octet is the lowest possible energy. All right, so as atoms continue to approach one another, and as they get increasingly close, there comes a point at which the two nuclei and the core electrons of each atom will actually start to repel each other. Okay, and this leads to higher potential energy, and the two atoms become less stable. So if the atoms get too close, the two nuclei, the nuclei of the two atoms, as well as all of those electrons, start to interfere with each other, right? Remember, like repels like. So leading to atoms that are less stable than original. So when is the bond formed? The bond is formed between two atoms at the distance between the atoms, where the forces of attraction, the attraction between the electrons of one atom and the nuclei of another, and the repulsion, meaning the nuclei from both atoms or the electrons from both atoms, result in the lowest, most stable potential energy. All right, so here's a little graph representing what we just discussed. So on the left here, we have increasing energy going up. And remember, the lower the energy, the more stable. And increasing distance between two atoms going across. All right, and as you can see in this area here, the atoms are very, very close together, and the energy, the bond energy, is very, very high. As the atoms separate a little bit, you end up, the energy goes down, and you end up down in this area here. And that is, that particular distance between the two atoms is the lowest possible energy, and that will be the bond length. Okay, that will be the perfect distance for those atoms to bond. If they get further apart, the energy goes back, it increases a little bit. So since the forces of attraction that stabilize atoms when they bond are attractions between electrons and nuclei, the greater number of electrons involved, that's kind of important, the greater the number of electrons involved, the greater the attraction, meaning that triple bonds are stronger than double bonds, and double bonds are stronger than single bonds, and shorter bonds are usually stronger than larger bonds. All right, on to the making and breaking of bonds. So the energy of making and breaking bonds. So energy is used to break a bond. So when you're breaking a bond, it's basically an endothermic process. You're adding energy. And energy is released when making a bond. So bond making is basically an exothermic process. Okay, let's talk about enthalpy of reactions. So delta H reaction is known as the enthalpy of reaction, or heat of reaction. And enthalpy is change in energy, or energy change. Okay, so we can calculate the energy change of a reaction. So how do you do that? First, you sum up the energy, required to break bonds. And because you're adding energy to break a bond, because it's endothermic, those energies are going to be a positive value. Then we're going to sum or add up the energy released when making bonds. And because when we're making bonds, we're releasing energy, that would be an endothermic process, those energies are going to be a negative value. And then you sum or add together the energy to break the bonds on the reactant side and the energy to make the bonds on the product side. And that will give you delta H of the reaction. So that answer there is delta H of reaction. All right, enthalpy of reactions continued. If the total energy needed to break the reactant bonds, endothermic process, is greater than the total energy released in making the product bonds, exothermic process, then the reaction or the system is endothermic and energy is absorbed from the surrounding, leading to a decrease in the temperature of the surrounding. All right, and here we have a little graphical representation. Another way to describe this. The enthalpy or the energy of the reactants is lower than the enthalpy or the energy of the products, which means when we're looking at the whole system. Okay, so we need to add energy to the reactants. There's more energy added to the reactants than released from the products, leading to a positive delta H, which means we have an endothermic reaction. If the energy needed to break the reactant bonds is less than the total energy released in making the product bonds, then the reaction system is exothermic and energy is released into the surroundings, leading to an increase in temperature of the surroundings. So in this case, reactants start at a higher energy level compared to the energy of the products. And this is because we are losing energy. Okay, let's practice a few of these. So what we're going to be solving for here is delta H of reaction. Okay, so this really isn't too hard. You're really just looking up numbers and adding them up. However, we do need to know all the bonds, which means we need to draw the Lewis dot structures for everything. So let's start with CH4. CH4 would look like this. And we're going to add to that three chlorine molecules. Which would look like that. And then we have CHCl3. So we'll have something like this. And added to that is HCl. Okay, so now that we have all of our molecules written in Lewis dot, we can actually look at the bonds and go from there. All right, so now we can start calculating delta H. So what we're going to be looking at is how much energy was used or added to create or to break the bonds on the reactant side. Compare that to the amount of energy released, which would be negative on the product side, and figure out the overall change in energy of the reaction. All right, so let me get rid of that. So, starting with the reactant side, we have, right here, we have 4 CH bonds. So the question is, how much energy does it take to break a CH bond? We have a table for that right here. And as you can see, a CH bond, it takes 414 kilojoules per mole of energy to break the bond. So we'll have 414 kilojoules per mole. And we have 4 of those. So we're going to be multiplying that by 4. And onward. The next molecule, we have just a Cl bond, but there are 3 of them this time, right? So 3 times, let's see how much energy it takes to break the Cl-Cl bond. And that's right there, so it's 243 kilojoules per mole. So on the reactant side, the amount of energy it takes to break each of those, all of those bonds is, we would sum those 2 up. Okay, on to the product side. Sorry, let me move this over a little bit, give me a little bit more room. Okay, so now on to the product side. We have another CH bond right here, and just one of them. So we already know that that one is going to be 414 kilojoules per mole. But remember, we're now creating bonds, which releases energy. So this 414 is going to be a negative number. And added to that, the same molecule also has 3 C-Cl bonds. So we need to look that up. C-Cl right here. It's 339 kilojoules per mole. So in the same molecule, we also have 339. Is that what I said? I just lost it. Yep. 339 kilojoules per mole. And again, this is a product. We're making bonds, which means we're releasing energy. And our last molecule is HCl, our HCl bond here. And let's see, that is 431 kilojoules per mole. And again, we just made that bond. It's on the product side, which means we're releasing energy. Forgot something over here. Go back to pink here. Remember here I had 3 CCl bonds. So we need to multiply this number by 3. All right. So now what we need to do is add all this stuff up, and we'll know what the overall change in the reaction was, the overall change in energy of the reaction was. So let's see, starting with the CH bond, I have 1656 kilojoules per mole, plus when we look at the Cl-Cl bond, 729 kilojoules per mole. Then I have, for the other HCl, I'm going to have negative this time, right? 414 kilojoules per mole. Minus the CCl bonds, the 3 of them, which is 1017 kilojoules per mole minus 431 kilojoules per mole. So real quick, just to make sure you're very clear on this, these are positive because we're making bonds, which means we're using or adding energy. And all of these are negative because we're breaking bonds. Or releasing energy. Okay, so at this point, all we need to do is sum all of these up. And I got, and I put this in my calculator, I got 523 kilojoules per mole. And sig figs, remember we're adding and subtracting here, right? It's all adding and subtracting, which means we look at digits after the decimal. None of them had digits after the decimal. Our answer has no digits after the decimal. So we have a total change in energy of positive 523 kilojoules per mole. So if the total change in energy is positive, that makes this reaction endothermic. It gains more energy on the reactant side than loses on the product side. All right, next we have HCN plus 2H2 produces CH3NH2. All right, let's start by doing the Lewis dot, and this time we'll do the energy for each molecule one by one. So HCN, let's go through the Lewis dot again. We've got H, C, and N. We start with the one that needs the most, and that would be the C. The next one would be the N, and the last one would be the H. So those can connect. Those can connect. So making this a little neater, we end up with H, C, N. Again, I'm not worrying about the valence electrons at this point. So next we need to figure out the energy added to break the HC bond. So that energy is still 414. And the energy needed to break the CN bond, and that's a triple bond here. So it's 891 kilojoules. You can see a lot more energy in that triple bond. No, what did I say it was? 891. All right, so this molecule altogether, the energy required to break the bonds in that molecule is 1,305 kilojoules. So I'll write that up here, 1,305 kilojoules. All right, how about breaking the bond for H2? H2 is just going to be H, so we just have a single HH bond, which is here, 436 kilojoules. However, there are two of them. So it's going to be 2 times 436 kilojoules, giving us 872 kilojoules to make or to break the bonds of two H2 molecules. So 872 kilojoules. And again, for the two we've just figured out, we are adding energy. All right, so now we need to figure out the energy needed to make the bonds in CH3NH2. And the way this is written kind of gives you an idea of how it should be set up. So we have a C, 3 H's and an N with 2 H's. So if we start with the C, we'll have C and then our N. So we'll have the N connected. And then there are going to be 3 H's connected to the C. And I'm out of room. Let me move this. 2 H's connected to the N, and the C and N will be connected together. All right, so now we need to figure out how much energy is used, or is released, when making 3 CH bonds. And let's see, that would be CH. It's this one here, bad color. Let's try that. This one here, 414 kilojoules. So we have 3 times 414 kilojoules, giving us 1,242 kilojoules. And we need to also figure out the energy released when making 2 NH bonds, which is here, 389 kilojoules. Giving us 778 kilojoules. So the total energy released when making the bonds to make this molecule, we'll add those two together, giving us 2,020 kilojoules. And this energy is being released, so it's going to be negative. So minus 2020 kJ. And now all we got to do is add all this stuff up, giving us a delta H reaction of 157 kilojoules. So this is an endothermic reaction because we used 157 kilojoules more energy to break the bonds of the reactants than the energy used to, the energy released when making the bonds for the product. Okay, that's it for today. Have a good one.